The next part of Taylor polynomials is expressing these polynomials as a series, because this is a sequence. It's just a bunch of numbers going on for infinity. So that means we can write it as a summation. And the summation is just going to be whatever pattern this follows, but instead of actual numbers that we write, we're going to put n here as in place for however many derivatives of it that we want in that series. So that's actually exactly what we did here. So all we need to do, so this Maclaurin polynomial as a series, and it was of e to the x, so this polynomial as a series is, you just write a summation and equaling. Now the thing about this is that we want to be careful about where we start n, because essentially the two numbers you're going to start at are either 0 or 1. And sometimes it takes a little bit of testing to see which one you're going to start with. So if we try starting at 0 of this, that means our first term is going to be n equals 0. So we put in a 0 here, we get 1. We put in a 0 here, we get 1. So that's 1 over 1, and let's look at the first term here. Yeah, the first term we put in there is a 1, so that means this works out. See, now if we, instead of a 0 here, we had a 1, that means this would be x to the first, which is x, over 1. So that means our first term would have been an x, but that's not our first term, that's our second term. So that's how we know that we are starting at 0. So this would be the Maclaurin series, this would be the series of this function. The Maclaurin series of that function. Here, let me move it so it's in line with everything else. Okay. So now this one would be a bit more difficult, and for things that look like this, we're not going to be asked to write, at least I'm pretty sure we're not going to be. We're not going to be asked to write this as a series, because in order to have this pattern, we have to have these f prime of c values, or f to whatever prime of c values in the series. So if we were to attempt to write it, it would look something like this. N equals, I'm just going to leave that blank for now because I'm not sure whether we're starting at 0 or 1. And I'm going to look, each of these has an x minus 1, and it's just increasing each time. So that means it's to a power of n. And then this factorial is also increasing by 1 each time, so that's just n factorial. But the issue now is these numbers come from these derivatives. So the only way to put them in there is to write f of whatever derivative at 1, because our c is 1. And then you could be okay, if I plug in a 0, f of 0, or f, no derivative, so just f of 1 is 0. And then this would be 0 factorial. This would be 1, because anything to the 0 power is 1. So in all, you just get that value, which is this 0. So we know we're starting at the correct number. But generally, you don't have this f of f to the nth derivative, f to the nth derivative in your series. But if you had to write a series for this polynomial, it would look like that. So let's go into a problem. Well, just to recap real quick. If you want to write a series, you want to write a polynomial as a series, all you have to do is find the pattern and just write the pattern into there. So we saw the pattern here is the x kept increasing by 1. The x exponent of the x kept increasing by 1. So that's how we know the exponent is n. And then the factorial of the term kept increasing by 1. So that's that n factorial. Okay, now let's talk about what is it called? Lagrange error bound or something? Yeah. Lagrange error bound. I'm gonna keep it in line, so. So this is the second error bound formula that we've learned. Remember, the other one was part of series, which was the, I don't know, series error bound. I forgot the actual name for it, but it was for series. So this one is essentially exactly the same, because these error bounds you're going to use the Taylor polynomials for, and you can write them as series. So, okay, it's just going to be very similar. So the error is written as r sub n of x. And this r, that's an ugly r. Okay, there we go. And it's going to be an absolute value. So this r stands for remainder, because what an error, this is equal, this is the error. Actually, I'm going to switch the places of these two things. So I'm going to move this down here. And then right here, I'm going to write error. So the error is equal to the remainder. And what the remainder is the absolute value of the actual function minus our approximation of the function. So remember, Taylor polynomials are approximations of functions. So the difference between these two things is the remainder. And the smaller that remainder is, the smaller the difference between our approximation and the actual value is. So essentially, the smaller the error, the more accurate you are. The more accurate this approximation is. And how we find this is, that's an ugly r. R sub n of x is equal to f of, I need more room. Put this in the middle. It's equal to f. Then the derivative is the next derivative. That's what that plus 1 is telling you. The next derivative at z. And z is just, what is z? So in an interval I containing c, then for each x and I. Well, I don't know. I'll think about it while we do this. And then the next factorial, that's that n plus 1 is, and then we have our x minus c, and then the next x minus c. So that's the plus 1. So it's very similar to the other series error bound, where we use the next term in the sequence to determine the error. And here we're using the next term in the polynomial sequence to determine the error. So it's like nearly the same thing. And we want it to be the absolute value of it. So let's just try a practice problem. We have a lot of room on this side, so I'll write it to the right of it. Okay. This is a lot of words, so I'm gonna paraphrase. So we're gonna have this number, we're gonna have this Taylor polynomial piece of 3. So this means the third derivative. And p sub 3 is the third degree Taylor polynomial I don't think polynomial needs to be capitalized. There we go. Nomial for f about x equaling 0. So essentially what this is telling you is that we have a Maclaurin polynomial, because is that what it's saying? Sorry, I'm not very practiced with this stuff, so why am I even teaching other people about it? But okay, I'm just gonna write the rest of what it says. So we have absolute value f of n of x, or is less than or equal to n over n plus 1 for the interval 1 to 4. And all values of x. I'm not sure what that adds though. And we're looking. Okay, so now this is the actual question they're asking. What is the smallest value for k, or of k, for which the Lagrange error bound guarantees that absolute value of f of 1, oh, I gotta move this, absolute value f of 1 minus p sub, oh my god, what am I drawing? P sub 3 of 1. This is an absolute value bar. It's less than or equal to k. Ah, okay. This is a lot of information. It all seems very confusing. But essentially, it's just asking us to find the error when we use when we're at the third derivative. Okay, so we want to follow our error formula thing, which is the same thing as remainder. So r of n of x. So I'm just going to rewrite it here, f of n plus 1 of z, and then x minus c n plus 1 over n plus 1 factorial. All I did here was I just moved this into the numerator. Okay, so what we're going to do is our n is 3. And we know that because we're at the p sub 3. So that's telling us the third derivative. And to find the remainder, we want to go to the fourth derivative. So we want to go 1 over. So in our case, it's going to be f fourth derivative of z. Oh wait, let me just write this down real quick. And then x minus, okay, it's, oh sorry, I shouldn't have blown into the mic. I was trying to get dust off my screen. Okay, it's x minus c to the n plus 1, but our x is 0, and our c is, I think our c is 1. I forgot to write here, it also converges at x equal 1. So maybe, I think that's our C. Okay, well anyways, x is 0, so I'm just going to write this in there first. So now we're at the 4th factorial. Okay, so now we're going to use this part. So f to the n, or f to the nth derivative of x is the same thing as plugging in n into here, essentially. So that's what we have right there. So when we plug in our n, which is a 4, that means we get 4 over 4 plus 1, which is 4/5. So that's going to take the place of that. And then our x is 0 and our c is 1. Yeah, I'm pretty sure it's because it converges. Sorry, you can't see that. Pretty sure it's because it converges at x equaling 1, so this is our 1. Oops. To the 4th power. And then we have our 4 factorial. So that's the answer. And this was a multiple choice question, and well, I mean, I guess they wrote it as like 4/5 times 1 over 4 factorial. But that's the remainder. So we are this number off from the actual value of f at 1. Okay, let's just really quickly go over what I just did, because I honestly, I know I'm a little confused too, but so it's asking us for this, and we want to recognize that it's asking for the actual function at 1 subtracted from the Taylor polynomial with the 3rd derivative at 1. And we see here that follows this. So we can say this is equal to this. Yeah. And then we just put the formula for r sub n to the x into there, which is this. And then we just plug in numbers. So we're at the 3rd derivatives, so n equals 3. Plug in the n, we get 4s all around. And then we use this information they give us to find that this part equals 4/5. Yeah, honestly, I'm not sure. I know that x equals 0, but I'm not sure what happened right here, but I just know it equals 1. Oh, I'm such a bad tutor. And then, so this is the smallest value of k, where our error is going to be less than that. So this is our answer. These are the same thing. Okay. Moving on. Is there more? Let's see. We're kind of at the end. So most of the stuff that we went over for Taylor and Maclaurin polynomials is just writing it as a series. So just as a reminder, to write one as a series, you're just gonna write a couple of terms of the polynomial out. So if they give you e to the x, you want to look for a pattern in the first few terms. So we wrote out, let's say you write out those 3 terms. You can already see the patterns forming with this is like x to the 0 here, and then x to the 1st, and then x to the 2nd. So okay, you know, that must be x to the nth. And then there's like a 0 factorial, 1 factorial, 2 factorial, so you know that in the denominator there must be an n factorial. So just write out, when you're writing something, a function as a series, just write out a couple terms of the polynomial version, and then look for the pattern and write it as a summation. And there are a few that you should just memorize. It's in your notebook. It's like a half sheet of paper with a bunch of, I'm pretty sure the title is Maclaurin series to know. It's just got a bunch of Maclaurin series on it that it would be helpful to know, because then you don't have to write out like the polynomial each time and look for the pattern and then write it as a series. Just memorize it, but I don't have that memorized because I haven't studied these yet. So this is literally me studying it with you. Okay, anyways. So the most important thing out of this is know how to do Lagrange error bound. I know I didn't give you a very good example, but essentially what you're doing is you have the Taylor polynomial to whatever degree, whatever like derivative, and then to find the error, you just go to the next, you just add one. It's like the next term. Okay, you see how this format is the same thing as this? It's just the next term in that series. So, fairly straightforward. And then just know how to write Maclaurin and Taylor polynomials. You want to list out a bunch of derivatives and then plug in whatever c value they give you. And then you just put it in a long line. Okay. Yeah, that's Taylor polynomials.